The recording's just started. So you may have to click to accept to be recorded.
It said, okay, continue, and I clicked that.
And just as a note, like the keynote tomorrow is not going to be recorded, just like, so you know. So you have to be here for it. That's Atif's.
Why is that? Why is that? Because he doesn't want it recorded?
No, I think it's just it's company policy, Apple.
Okay. Okay.
Sometimes, I mean, we've had in another conference I organized, Facebook also was very not interested in things being recorded sometimes. So.
Oh, and that changes.
Yes. Apples and tomatoes.
Well, in any case, I think it's legal departments 100 plus persons, and that makes a difference.
Well, you know, AT&T had a big legal department, but they were happy to let anything be recorded, anything be published. I never once had any issue with that. But it was a different philosophy.
And a different time. I mean, the visibility of those things before 2000 were different than they are today.
Well, but I was there much later than 2000. Okay, I was there, in 2012, and there was never any issue. But AT&T had a certain, they viewed everything as being for the common good. Honestly.
I think there's
I think we'll get started.
Sorry, I was just continuing this conversation. I will stop so she can start.
Yeah, I think we'll get started. People are starting to come in. If I could ask everyone who's not speaking to mute in the usual style. So, Carmen, I'm here with Heather Miller. We're the program co-chairs for the SEIP track at ICSE, and we have 3 invited distinguished speakers for you today, tomorrow, and on Friday. And I'm very pleased to be able to introduce the first of these today, which is Elaine Weyuker. Elaine actually needs no introduction. Many of the people may be here for their first ICSE, so let me just give you a brief context so that you understand why it is that Elaine is a distinguished invited speaker in this industrial track. So Elaine has actually won both top awards in software engineering, the IEEE Harlem Mills in 2004 and the ACM Outstanding Research Award in 2007. And her career spans 5 decades of contributions in software. In the 1970s, she was working chiefly on program schemas and the mathematical theory of computation, which led her to lay some of the foundations granted in software testing. So things like the Oracle problem, data flow testing, test adequacy criteria, all of these things you really owe to Elaine. And then in the 1990s, she was one of the pioneers of empirical approaches to engineering, which carried out throughout the rest of her career with contributions in fault localization, fault prediction, and empirical software engineering. If I go on and give all of the contributions that Elaine has made over the, won't be any time for her to speak. So rather than doing that, I will now, with many thanks, we'll hand over to you for your keynote talk.
Okay, let's see. Okay, well, thank you so much, Mark. I'm really honored to have been invited here, and I'm really pleased because if there's a single thing that has driven a lot of my career, it's doing first-rate research which can transition into practice. And I think that that's a critical focus that not enough software engineering and software testing research has made. So let me say something about where I've been. And the reason I mention these is because it really does influence what my positions are and why I think what I think. So I started as a math major in college, and I graduated, and I went out and got a job as a programmer in industry. And I did that for roughly a year, and then I went back to graduate school. And I got a master's degree in computer and information sciences within the School of Electrical Engineering. And that's important because when you study computing within an engineering environment, it tends to be much more pragmatic than if it's within the School of Arts and Sciences or within a mathematics, uh, say, department or institute. When I finished my master's degree, I then again went out into industry and took a job as a systems engineer at IBM. And my job as a systems engineer was to work with IBM customers. And after a year to a year and a half, I was offered a position as a full-time faculty at a teaching college within the City University of New York. And I did that for 6 years. And for the entire 6 years, I was the entire computer science department. Um, I taught absolutely everything, ranging from symbolic logic, which was really a pure math course, to switching theory and automata theory, which were really engineering courses, and everything in between, all levels of programming, compilers, operating systems, anything that was taught in computer science, that was me. I also taught operations research, which was somewhere between computer science and engineering. At the end of 6 years, I decided to go back and get a PhD because I wanted to be a more traditional academic. I wanted to teach at a research institution and do research. And so when I finished my PhD, and this time it was in computer science, a separate computer science department in arts and sciences, I got a tenure track position at NYU within the Courant Institute of Mathematics. And NYU is what's called an R1 university, a major research-focused university. And to be honest, I expected to spend my entire career there because the way my view was that you got a PhD to do this kind of position. And although my dissertation was very abstract mathematics, foundational for computer science, I very quickly moved into software testing, which is another long story. But, and in a lot of ways, I was very successful. I became a tenured full professor. For 6 or 7 years, I was also director of graduate studies. I got research grants pretty much every year, mostly from NSF, but also in addition, many years I also had funding from NASA, from the Office of Naval Research. So from the funding point of view, I was a great success. I was an editor of all the major journals, including being a founding editor of several of them, including TSE, TOSM, JSS, Empirical Software Engineering. And I was either a founder or the program chair or program committee member of all the standard software engineering and software testing conferences, including ICSE and ISTA and ISRI and ICST, etc. So I was publishing widely. I was getting funding. I loved teaching. I loved working with my students. But the one thing I was constantly unhappy with was I was doing software engineering research with no software. Basically, the way all academics were doing it, with toy software. And there was something sort of constantly unsettling about that. And over the years, Bell Labs would periodically contact me and try to recruit me. And I'd say, no, 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 I'm an academic. I'm not interested. And finally, after I'd been at NYU and was a tenured full professor for 16 years, a vice president called me and said, look, let me make a proposal to you. You're tenured. Why don't you take an unpaid leave of absence for a year? We're making you a full-time permanent position at the labs. We think you'll love it. But if you don't like it, then you'll just quit and go back to NYU, and you'll have learned nothing. You'll have lost nothing. And I said, well, if I went to the labs, I'd like to be in the research division, yes, but I'd also like to have a way of really regularly interacting with practitioners, because that's what would make this an interesting position for me. And he said, well, that sounded great to him. And he put me in contact with the person in research, the director who headed technology transfer. And when I told him what my vision was, he was actually thrilled. He said, I can't get anybody in research who wants to have anything to do with practitioners. So the fact that you do is thrilling to me. And he says, I can guarantee if you come here full time, I will get you whatever interaction you want. And so I did what they suggested. I took an unpaid leave for a year from NYU and went to the labs. And I decided the first thing I would do was he introduced me to the heads, the directors for the two main software development organizations in New Jersey for the labs. And one of the things they told me was that they had 450 million lines of code that ran 24/7. And if I wanted to be involved with any of those projects, just say the word and they would arrange it. And so I proposed that what I'd start doing was giving talks aimed at practitioners, either developers or testers, about my research, and do sort of what I thought of and what the politicians call a listening tour. So I give a talk about my ideas on software testing and get feedback to the extent, to what extent they thought that might be usable in their organization. And if not, why not? I could speak with small groups. I could speak with big groups. If they needed somebody to do assessment or measurement or metrics, I'd be happy to work on that as well. If they wanted me to evaluate commercial tools, I'd do that. I was interested in hearing what their issues were. And so that's how my career at the labs began. And for the first, I'd say 6 months, it was just me being embedded with various development organizations and development projects, telling them my ideas, listening to what they wanted and what they thought about my ideas, and identifying people that I could collaborate with. And I can say for what turned out to be the next 20 years at the labs, every single thing I did during those 20 years involved either a practitioner, collaborator, or working with their systems, having a large industrial empirical study that evaluated how successful my proposed techniques were, etc. And so after a second unpaid leave of absence from NYU, so I was there for 2 years where I was technically on leave from NYU. I resigned from NYU and became a full-time permanent and continued only as a full-time permanent employee for the next almost 20 years. In 2012, AT&T, for a variety of reasons, started to shut down their research organization. By this time, Tom Ostrand had moved there from Siemens Research. He was my main collaborator. We had met as graduate students, so we pretty much collaborated on and off for most of my career. He's also my husband. And so we both got fired on the same day in 2012. There are more polite ways of describing it, but the bottom line was they were shutting down research and we got fired. A lot of people heard that I was available and expressed interest. The problem was that I was, for personal reasons, we could not relocate out of the New York metro area. And also at this stage in my life, I was only interested in doing what I was interested in doing. And so for a variety of reasons, nothing really was felt like a good fit for me at that time initially. Until Sigrid Eld, and if you're here, Sigrid, hi, popped up. And Sigrid is a software testing researcher and practitioner at Ericsson. I'd known her for many years. I had been the opponent on her defense, and she introduced me to people at Mälardalen University in Sweden. And I'll speak about the details later, but in 2013, I started a very unusual position in Sweden while living primarily in the US. Anyway, the picture to see is that through my entire career, I have ping-ponged back and forth between industry and academia, and that truly informed the way I view the way I think research should be done in a pragmatic field like software engineering and software testing. So in 2010, while I was still at the labs, I wrote a white paper for the Foundations of Software Engineering research meeting, which was a small meeting underwritten by the National Science Foundation. And in this white paper, I said I was really concerned about the software testing research community because although the people were very smart, in many cases they had lots of very interesting ideas. So there was nothing wrong with the research community per se. What was wrong was that, first of all, they weren't addressing the kinds of critical problems that I was hearing from industrial folks were really important to practitioners. And what was even more disturbing to me was that in many cases, not only weren't they addressing them, but they were totally unaware of the importance of these kinds of issues. And I went on to enumerate a number of specific topics that I just was not seeing anything in the research literature, but yet was increasingly important in the world. So the first thing was embedded systems. Even by 2010, embedded systems were everywhere. So we drive cars and there are millions of lines of code in them. And we have refrigerators and they have software in them. And of course, airplanes, well, whew, and our thermostats, and basically everything, all these embedded systems that are fundamental in our life are being controlled by software, and yet we're not talking anything about how one tests that kind of software. And we talk as if the only software is software that runs on a computer, and not only that, but it's basically transaction processing software. You have some inputs, the computer does some kind of, or the software does some kind of computation or string processing or database operations, and then it outputs the answer. And so much of software is not like that, and yet we aren't talking anything about how would we validate those systems. Another thing is, if you want to get practitioners, if you want to get your software into practice, you have to convince practitioners that your ideas will run at scale, will run in their kind of environment. And as long as all you're presenting are toy, is showing how how your techniques work on toy systems, it's not convincing. We need industry-based systems which run at scale, which have timing constraints, etc. Another thing is, so many of the techniques that people propose are done manually. And when you have hundreds of thousands or millions of lines of code, which so many systems have, we know you're not going to do anything manually. You need tools. They need to be easy to use. They need to run at scale, and they need to meet timing constraints. And just to give you an example, for the last 10 years that I was at AT&T, Tom Ostrand and I focused primarily on software fault prediction models. And so what we did was we started out with one real system that had been in the field, that was roughly 500,000 lines of code, had been in the field for 4 years. So it had a long bug history, which was accessible through the repository. And so what we did was manually go through the repository and identify all the bugs and try to identify which entities, and at AT&T, the entity that was the main entity were files. So bugs were recorded at the file level. So we tried to identify what were the most buggy files throughout the system's history in the field. And then we said, now what do these buggy files have in common? And we were doing all of this manually. And then we started running correlations, and we identified a set of properties that seemed to correlate with fault proneness, again, manually. And then we built statistical models that we thought could be used to predict which would be the most buggy files in the next release of the software system, again, manually. And when that seemed to work, we built a small prototype tool. The tool ran at scale, but it was a prototype in the sense that it had a crummy interface, but it was something that we could go to practitioners and show them how it would work on their 2 million lines of code. And so we went around with our dog and pony show, showing them how our tool worked. And what was important to them was to see on the fly, we could hook it up to their system, make predictions for whatever release they wanted us to make predictions for. They got responses in under a minute, and that was important, even though they had 2 million lines of code. And once we started showing them what we could do with our prototype tool, we got interest, and then we got a professional toolsmith, which we were not, to build a tool that could be embedded in the dashboard that every practitioner had access to, and therefore could be moved out into practice. But it took a lot of time and it took a lot of effort to do that kind of thing. And what we're not seeing is people building tools and trying to show that it can be run at the kind of scale that practitioners need. The other thing that concerned me, and this is in the 2010 paper, was that um, in the software testing research literature, testing was equated with functionality or correctness testing. And what I was seeing in practice was uh, the big problems that practitioners had was not that they ran a test case and they got the wrong answer. That was not the problem. The biggest problems that they were seeing, or that were what I would characterize as performance issues. So the system was built to run with 1 million simultaneous users, but this has been a great success. And now you've got 10 million users. And whenever you have a spike of users, the system crashes, or you start throttling users. They're told, come back later. And that's completely unacceptable. And so we should be testing all along for performance. Or you have a system that works perfectly on any possible input, but you don't get the necessary stimulus response time. You need to get a response in under a second, and it takes a minute, or it takes 2 minutes. And let me give you a concrete example. You have an onboard collision avoidance system in an aircraft. It's supposed to alert the pilot as soon as it detects that the nose is at too steep an angle, or you're descending too quickly. And it's supposed to alert the pilot, who's supposed to instantaneously take corrective action. So that's great if it tells the pilot in time for the pilot to make a corrective action. But if it takes 2 minutes, the aircraft is now in a position that can no longer be corrected, and therefore you have a crash. So there are all kinds of situations like this where the program functions perfectly. Every input works correctly, but not with the response times that are required in all cases. Another thing that we weren't focusing on is software safety. Another thing I identified was testing for vulnerabilities. We were not looking at the security realm, which was different than correctness. Okay, other issues, I was concerned that who was doing the teaching, what their experiences were, and how we were training our students. Now, I don't think that a university is a trade school. I don't think it's our mission to train students to run on your company's software, etc. On the other hand, who are most of our academics? Most of our academics, even today, and certainly at that time, were people who were the best students. They graduated from college and went right to graduate school and whizzed through and got their PhD. And what did they do? They went out and got a tenure track position, or they got a postdoc at an academic institution in anticipation of getting a tenure track position. And so what are they doing? They have no pragmatic experience. So they're teaching our students, and the bulk of our students, after all, are not going to get PhDs, are not going to become researchers. They want to go out and get a good development job of some kind. They want to become a programmer or a tester or something or other in industry. They want to earn a good salary. They want to have a nice life. They don't want to do research. This is not their vision. And yet, instead of telling them what the realities are, what it feels like to work in a big team, because no organization, no individual builds a 500,000 lines of code. You're part of a much bigger team with real immutable time constraints, and your boss doesn't want to know that it's somebody else's fault that you didn't meet your deadline because he wasn't working hard enough. Your boss wants, it's your team's responsibility and your responsibility. And so few of our students come out with a bachelor's degree understanding what life will be like. And this is the most common complaint I hear from industrial partners. They say, they're not prepared for our realities. And it's because our educators do not have any pragmatic experience, I feared. Then in 2011, I was invited to give the keynote address at the Empirical Software Engineering Conference. Again, I was thrilled. I felt that doing empirical studies was critical for our research. It was the first step to getting our research out into practice. But and I said in 2011, roughly a decade ago, while there's increasing amounts of empirical studies being done in the top venues, and we have this first-rate journal and first-rate conferences that focus on empirical software engineering, which is great. Too little of that empiricism is being done at scale, is being done at real systems containing real defects. The vast majority of what I was seeing were academics doing empirical studies on toy software with synthetic bugs that were injected into the software, often one at a time. And as anybody who builds big systems knows, that's not reality. I went through prior or in preparation for this keynote, I went through the prior 5 years of all the top journal and venue software testing papers. And what I found was the vast majority of papers still had no empirical studies. And if they did, they were almost invariably done on these toy systems. And the ones that sort of made it sound like they were doing empirical studies on real industrial systems use the so-called Siemens suite. And for those who are not familiar with this, this was a set of 6 or 7 toy programs, a couple of hundred lines of code typically, that were written by Tom Ostrand, who was at the time at Siemens Research, and Tarek Goradia, who had been my PhD student at NYU, who, when he completed his PhD, went to work for Tom at Siemens Research. Both really smart guys, but they were in research organizations, and they had developed this set of toy programs to do a research, a very interesting research experiment at ICSI, which was later published in TSE. But the point was to compare a variety of different testing techniques. And so what they did was have this suite of programs, and for each one of the programs, they prepared a set of faulty versions. Each one had a single fault in it. So they now had a big bunch of programs, a correct version of each one, and a whole bunch of buggy ones. And they compared which techniques were capable of finding which bugs. And that's all they were. They were toys with single synthetic bugs. And a lot of people asked Tom about the programs, and he said, yeah, instead of you writing your own toy programs, yeah, I could package them, and he freely distributed them with the caveat that they were just toys that he had developed, and that the bugs were really synthetic bugs, and that's what they were. But yet people were using these as if they were some kind of a real gold standard of empirical studies, and that concerned me. So now we're up to today. Okay, it's still rare for me to see academics with real industrial experience, so I still worry about how we're teaching our students to be software engineers and to be software testing research, to be software testers. And I decided to make sure that to look at ISTA. I was one of the founders of ISTA. I still consider it the best, or certainly one of the best, software testing conferences. My most recent paper was published in ISTA 2020 with some of my Swedish colleagues. So I looked through the program of the most recent instance, which was ISTA 2021. Almost every paper was written solely by academics. There were a handful of papers that were co-authored by that included at least one co-author from industry, even including industrial research, which often are completely closeted research organizations. And I looked at all the topics that I considered really important, that I talked about more than a decade about, and nobody was still talking about testing embedded systems. They still weren't talking about testing for performance. And one of the things that really surprised me was that there didn't seem to be any papers on what I would call intermittently failing tests, or irreproducible faults, or non-deterministic faults, and which are sometimes called flaky tests. And I really hate the use of that word because it makes it sound like the tests are bad. and in fact, a lot of the flaky literature talks about them as if they are bad and tells you to get rid of them because they're no good. And in fact, every practitioner tester knows that even though they detest these irreproducible faults, and they're the ones that bite you in the backside, and that they're just impossible to deal with, they are real bugs, and they're the ones that you really have to worry about because they're going to crop up. You know that they really happen, and they're the ones that are going to crop up when you're least expecting it, and really are potentially catastrophic. So just to give you a picture, typically a software tester runs some test cases, observes something that they consider not proper. They document this in some kind of repository. They say, okay, this is what I did. This is the test case I ran. This is what I observed. This is what I expected to observe. And then they send it back to the development team to fix the problem. The first thing the developers do is try to recreate the same situation, and they can't. And that's when the difficulty starts. But the fact of the matter is, you know that sometimes under these circumstances, the system will fail, and they have to be found. And one of the problems is that you frequently have bug interactions. We don't have single bugs isolated. We have all kinds of interactions going on in large systems. Okay. And 2022, ISTA 2022 does not have the program out, but the PC is listed, and roughly 90% of the 2022 PCs are academics. And what kind of papers do you think they're going to like? This is a very, very prestigious conference. It's a very difficult conference to get a paper accepted at. What are the papers they're going to like? They tend to like nifty new ideas, which frequently do not have the next step associated with them. Okay. Okay. And so why doesn't everybody do what I want them to do? Well, first of all, there's little incentive to partner with companies, especially given that it's very difficult and very time consuming. I can say without hesitation, I spent the first 6 months to a year that I was at AT&T doing nothing but getting set up to do what I felt would be, first-rate research, making these connections. So it did give me a dry spell. When you're an academic and you partner with a company, there's always the issue of intellectual property. Maybe we do something great. Who's going to own this? Who's going to be able to monetize this or stop other people from monetizing it? That is an issue. Also, when what you do is software testing research, it's very hard to convince a company to let you, an outsider, see their bug data or the security flaws that they have, because even though you sign a non-disclosure agreement, they don't want an outsider to know what their real problems are. So that's the problem. Now let me go back to where I was and about today. So as I mentioned, in 2013, after I left the labs, I started as a part-time faculty in Sweden. And the agreement that I had was I was a professor, but I only went for a couple of weeks each semester. And my mission was to supervise and mentor PhD students, postdocs, young faculty, help them get going with their research, collaborate with them, and also with local industry. And I would go for 2 weeks during the year, during each semester, I mean, and we'd work very intensively during those 2 weeks. And then I'd go back and we'd continue having meetings. At that time, we were using Skype. We'd write papers jointly using Dropbox or Google Docs or something like that. We were publishing on a regular basis. We were interacting with local industry, because the way that most of the Swedish funding agencies worked was they required that each proposal get a couple of industries, a couple of companies to, in a sense, endorse the research. And the government is funding the research, but the companies say, we think that if this research is successful, it would be useful to us. And therefore, it's worth spending taxpayer money on this. And they're usually expected to put their money where their mouth is. And they're not funding the research. But so what do I mean, put your money where your mouth is? Well, say if you're testing embedded systems, you need some kind of equipment. They provide this expensive equipment, or they let you come and work in their labs on their equipment, or they'll guarantee a certain number of engineer hours per week, per month, per semester, per whatever. And these engineers will collaborate with you, will help migrate your prototypes into practice, see how well they work, tell you what kinds of things they need, and in that way, totally inform the research. They might give you access to their data, which you need to do something. So there are all kinds of ways that companies can interact and do interact because of the funding model. And so typically in my 2 weeks per semester of visit, I would not only spend it working with the team of people I was collaborating with and mentoring, but also with going to industries, giving talks, talking about our research with them in fundamental ways. In addition, so that worked great, and I did that from early 2013 through December 2020, at which time funding for my group was running down, and but more to the point, the pandemic had hit. I had planned to be there May 2020. I hadn't been there since for the year before, because I hadn't been there since the previous September 2019. And there was no prospect of my coming. And so basically in December 2020, after 8 years of what I think was a very, very successful interaction, and one that I loved a great deal, my relationship with Maladalin ended. However, in late 2016, the dean of the College of Engineering and Computer Science at the University of Central Florida approached me and invited me to do the same kind of thing, working for him, engineering college-wide at UCF. And to give you a picture of UCF, it's the largest university in the US. There are more than 71,000 students on one campus. The engineering school has between 14 and 15,000 students at any time across the different engineering and computer science disciplines. There are something like 200 full-time tenure-track faculty, plus a lot of full-time lecturers and part-time faculty. And so it's a very, very large, complex institution. And he asked me, could I do the same kind of thing that I was doing in Sweden for them? And so my mission at UCF, I started in the beginning of basically, my first visit was in February of 2017, and it continues now. I just ended a couple of weeks ago my most recent visit. I have a commitment to spend 2 weeks per semester on campus, and primarily I mentor young faculty and also women and underrepresented minority faculty across the engineering college. For people that I have close technical relationships, I tend to mentor them on their technical work, and I generally meet with them once a week all year round. When I'm not in residence there, I'm in New Jersey, and we meet via Zoom or something like that. For other faculty, I frequently meet with them once a month. Some I work with every week. Some I meet with once a semester, and some I meet with on demand. When they have a particular issue they want me to help them deal with, we set up a meeting. And for women and underrepresented minority, I help them try to solve problems that tend to be unique with being a minority within the institution, and for women, they're minorities in an engineering school. I also help young faculty of all kinds figure out how to manage their time, so that they are successful in funding. I sometimes read proposals or submissions before they submit them, so that I give them feedback as if I was a reviewer, and help them help their proposal or journal submission or whatever get the negative feedback that they might get, so that they can fix it and it can be more successful. All right, what kind of things can we do to get things better? Well, I wish that government funding agencies would do things like what I saw in Sweden, to foster interactions between industry and academia for the common good. Once the pandemic hit in March 2020, and I was there, March 9th, 2020 was my last day of my 2-week on-campus period. The university was shutting down. I flew home, went into immediate lockdown in New Jersey. And what the dean did was he started a weekly seminar, which was open to the public and occurs every week. And initially, 3 faculty members from across the college gave small presentations on their research, and this was open to not only everybody in the university community, but also there are a lot of local industries, UCF is in Orlando, which is along what they call the Florida High-Tech Corridor. There's a lot of NASA people working in conjunction with Cape Canaveral, for example. There are a lot of high-tech industries. There's Siemens, very local. There's Harris Corporation. There's Lockheed Martin. There are many others. And they were invited, come and listen to what our people are doing. And the goal was to let people know what your colleagues are doing, and to let people know, and to let outsiders know what's going on.
Elaine?
Yeah,
sorry
I'm.
I just wanted to mention you're at the 5-minute mark. Yes.
Yes, I know. Okay, I'd like to see funding agencies. So those are the kinds of things I think people could do. I'd like to see funding agencies fund academics to spend a semester or a year in industry, not in industrial research, but in industry, in order to help them understand what their students are going to be doing, and also improve their research. I think the good news today, and there is good news today, I think the fact that we have a conference like this where 80% of the papers are co-authored by at least one industrial author is fabulous news. And the fact that it's part of ICSE is fabulous news. And the last thing I'm going to mention is the Computer Research Association. The CRA is a consortium of research universities and government entities in North America. And they've just announced an industry thing which aims to engage, convene, and enable. And I could have written this, although I knew nothing about this except that I saw an ad for it. Their first meeting is going to be in July 2020. It's doing exactly the kinds of things I've been advocating for the last 20 years. And so we're used to seeing things move at a glacial pace, and we know how quickly glaciers move, except now, because of global warming, glaciers move much more quickly. And this is a picture I took about 3 years ago in the Patagonia region of Chile, where in front of my eyes, the glaciers were breaking off. And this is what I was seeing. So I hope that we will continue at a glacial pace, but in the new reality of what glacial pace means. And so with that, I thank you all. That was fast, huh?
Thanks very much for your talk. So we have some questions already in the chat. So if you have a look there, they're highlighted in pink. So the first one is from Stefan Lip. Identified areas that are important. And Stefan is asking, which of these areas do you feel has been successfully tackled in research in the meantime, and which not?
Well, as I said, I looked at 2021 of ISTA, and in fact, none of them were being tackled now. And my paper with my Swedish colleagues in ISTA 2020 did address embedded systems, but we were the odd man out, and we did. And for years, Alberto Evritzer at AT&T and I worked on performance testing, and I gotta tell you, nobody was interested in it. And one of the real eye-openers was we wrote a paper and submitted it to ISTA one year, and it was rejected without review because it was viewed as, and this was a software performance testing paper, it was viewed as outside the scope of the conference, which was shocking. I can deal with people thinking that my ideas are not great. I can't deal with people not understanding that performance is really a critical part. So I guess I see, I haven't seen enough of an awareness of a lot of the issues. There is increasing awareness of security issues for obvious reasons. But a lot are